Swayam Prabha. Digital India. Educated India.
So now we are moving to another set of advanced finishing processes which uses abrasive particles, that is called magnetic field assisted abrasive finishing processes. So in this category there are varieties of processes ranging from magnetic abrasive finishing to magnetorheological finishing to magnetorheological abrasive flow finishing and so on. So in this particular class what we are going to see is magnetic abrasive finishing and some of its allied processes such as magnetic float polishing, magnetic abrasive deburring and other things. So the plan of the lecture goes like this. So introduction to advanced abrasive finishing processes, what are the various abrasive finishing processes, then introduction to magnetic field assisted finishing process, then basics of magnetic abrasive finishing process, how it will be working and what is its mechanism, how about whether you are going to finish a magnetic material or a non-magnetic material, how the field of lines will emerge, and other things, and magnetic abrasive finishing of ferromagnetic and non-ferromagnetic materials, where the mechanism of material removal, how it will takes place, how the flexible magnetic abrasive brush will form and other things. Flexible magnetic abrasive brush, how this particular brush is responsible for finishing. So magnetic abrasive deburring process as well as magnetic float polishing process. Just we see the glimpse of these particular processes at the end. Okay. So introduction to abrasive finishing processes, where to finish the surfaces in nanometrical range, it is required to remove the material in the form of atoms individually or in the molecules or in groups of these atoms or molecules we have to remove. The classification of advanced finishing processes, or what we have seen in this one, is abrasive finishing processes. So the conventional finishing processes followed by polymer assisted abrasive finishing processes, which we have studied only very few material about this particular process, like abrasive flow finishing process, polymer rheological abrasive fluids or medium, and its rheology and its capabilities and all those things. Polymer rheological abrasive fluids and its based finishing process itself is a very vast course. So just I gave you glimpse in this particular course. However, if at all people are interested extensively in this particular course, there will be an advanced version of this course where polymer assisted abrasive flow finishing processes. Okay, so it is a 10 hours course where you can do this particular course and you can learn more and more. So that particular course is mostly about the basics plus advances also. So that will be mostly useful for doing your BTech project work, MTech project work and PhD oriented work also. Okay, so that's why I have not touched much on this polymer assisted abrasive flow finishing processes or polymer assisted abrasive finishing processes. However, I am going to give you some of the introductions about the magnetic field assisted finishing processes, where magnetic field is used to control the forces of this particular process. So why advanced fine finishing process is required? Normally this process is labor intensive methods, because the final operation that one can do on particular component or particular workpiece is finishing operation in a mechanical spectrum. Okay, so you have to acquire the tolerances, you have to acquire the finishing and many things. For this purpose, what all you require is you need to choose a very highly skilled labor, wherein if you are going for the skilled labor or very high skilled labor, the salary of the skilled labor or very high skilled labor will goes up. So, the product cost goes up. Difficult to controlling forces, because as I said, even though very experienced person operates with a hand or something, what will happen? Today he will be fine, so he will be finishing properly. Tomorrow assume that he has a quarrel with a family member like wife or something. So, he may come, I'm just for example I am giving, don't take in otherwise. So, he may show the anger on the component. So, it will be lot of problem for the surface finish and other things, because it is not controlled or automated by a mechanized way or a electronic controlled way. It is a human. So, emotions also will be a part of finishing forces. So, complex geometrical shapes, some of the conventional finishing processes cannot do for the complex shapes like any knee implant, hip implant and other things, because the conventional abrasive finishing processes uses the solid type of tools like grinding wheel, honing wheel and other things. So, precise control of the finishing forces is not achieved because the solid to solid contact, if you are going for a grinding wheel, it is a solid to solid contact between workpiece and a grinding wheel. So, the forces will be enormous. So, you need minimum forces and you have to get the surface finish very good, but we do not bother about MRR. We are not at all interested in a finishing process about what is the material removal rate. So, nanometer surface finish, because we want in a finishing process is the surface finish that one can achieve on the component, not the material removal rate. Need of high precision manufacturing is to improve interchangeability of component. If you are finishing and everything is good, so interchangeability is good. Improve the quality control. So, some of the components in a conventional finishing processes may reject in the quality control examination. So, if you are going for advanced finishing process, the surface finish levels will be enormously high. In that circumstances, what is going to happen is you are going to get the good quality product. So, it can pass the quality control test. Long wear and fatigue life, because your surface peaks are very less. I mean to say peaks and valleys are very less, because of which what will happen is you are going to get good life. So, finishing ability of various abrasive finishing processes, if you see the spectrum, the serial number followed by the finishing process, workpiece material and the surface roughness value. Okay. So, the surface roughness value is given in the nanometers. So, if you are going for grinding, you can achieve this particular value like 25 nanometers if you are going for micro grinding or very super finish type of grinding and other thing, honing and the lapping process. And if you see abrasive flow finishing process, the best surface finish achieved by extrude hone company is 50 nanometers. However, there are some reports that the people have done extensively in this one and they have achieved below this on some of the common materials also. Magnetic abrasive finishing, which we are going to study in this particular class, is this magnetic abrasive finishing process on stainless steel. The people achieved 7.6 nanometers. Magnetic float polishing with cerium oxide as abrasive particles, with the cerium oxide as abrasive particles achieved 4 nanometers, which is a very good. This particular part also we will see in this particular process. Magnetological finishing process achieves the surface roughness of 0.8 nanometers. That means that sub nanometers range can be achieved. Elastic emission machining is less than 0.5 can be achieved using elastic emission machining, and ion beam machining and other things can be achieved 0.1 nanometer and other things. This is the beauty about the some of the processes that are given in the literature. So, this some of the slides is a combination or the study of many research papers and some of the books also. So, the slides comprises not only the reference books, but also it includes most of the research papers also. So, people who are following this particular course should understand that they have to read the research papers also along with the books for your basic understanding and advanced understanding. However, what I want to tell at this particular point of time is that the questions that you are going to get from the examination, because keeping in mind of bachelor students, master students and PhD, apart from these there are many faculties who are also doing this particular course. Keeping all these people, so emphasis is given to the students. That's why the question papers consist of mostly basics. So keep the basics ready. At the same time, some of the advanced questions also will be there. So if your basics are proper, then you can answer the advanced questions also. Okay. So ultra precision machining, if you see the Taniguchi et al., they has given a table where the machining processes are classified into 3 categories. One is the conventional machining, second one is precision machining, and the third one is ultra precision machining. If you see that machining accuracy versus number of years are the as the time passes, so the machining accuracy levels are coming down, the surface requirements are coming down. So new workpiece materials are coming up, the surface finish levels are enormously coming down. Okay, so for that purpose, what the people have to find is, we have to find new type of abrasive finishing processes where you can achieve very good surface finish on the advanced materials for any type of applications. Okay. If you see the normal machining or the conventional machining, the surface ranges is from 100 microns to the range of 1 micron as it progressed from 1940 to 2000. Okay. Currently we are in 2018, so it will be still lower. Okay, it may go like this. Okay. So in the precision machining processes, if you see, the range is below 10 micrometers to approximately approximately slightly above 0.1 micrometer. Okay. So as it reaches to 2000, if you are looking at 2020 and other things, what will happen is it may go below 0.1 microns also. In ultra precision machining processes, if you see, so it is also starting from less than 1 micron and it is approximately 0.001 as per the year 2000 is concerned. If you are seeing as per the current scenario, what is going to be is, it might have gone, but it may not, you cannot extrapolate in the same tangential way because it is completely randomized. So it will, you can say qualitatively that it will be below than what it is in 2000. That okay. So some of the normal machining processes like turning, machining, turning, milling, grinding, CNC, lapping, honing, jig boring and other things will come under this category. And precision machining, normally precision grinding, super finishing, ultra precision, diamond turning and other things. X-ray lithography, ion beam machining, ion implantation and other things, all this will go for the ultra precision machining. Okay. So some of the abrasive processes also will be in the range of the precision machining to ultra precision machining processes. Okay. That means that whatever you are going to study in the conventional way, that means like grinding and other studies which you have seen in the early part of this particular course, come under the conventional machining. The second part what we are going to see, like polymer assisted abrasive finishing processes and magnetic field assisted abrasive finishing process, come under the category of precision machining to ultra precision machining. Okay. So if you can see here, elastic emission machining is what we have studied, and MAF we will study, and so many things like elastic emission machining, the electrolytic abrasive machining, these are all which we have not studied, but however some of the processes that we have studied is elastic emission machining. This follow in the surface roughness range of 10 to the power 0 and so on. So we are not as most of the processes are not relevant to abrasive processes like single point diamond turning, CNC metal cutting and other things which will not come under abrasive finishing process. That is why we have not studied ion beam machining and all those things. That is why what I can say is that among our processes, we have one process that comes is elastic emission machining and other things. Okay. The classification of this polymer assisted finishing processes and magnetic field assisted finishing process, we have studied the abrasive flow finishing, which is a main part of polymer assisted finishing process, and extensive to it, if at all anybody is interested, as I already mentioned, there will be a new course which is floating for 10 hours, that is polymer assisted abrasive finishing processes, where extensively people will study about the polymer rheological abrasive fluids, how the mechanism of material removal, what are these allied processes and etc. will be studied in this particular course. Okay. So, do not think that abrasive flow finishing is the only process that will be covered in that one. It will cover lot of processes like elastic emission machining that we have seen in the previous slide, and elasto abrasive finishing, micro AFF, orbital AFF, so on. There will be a pitch polishing where the polymer oriented will be there. There are abrasives that are made up of polymers, so on. You will study in 10 hours course, that will be for 1 month and other things. Okay. If anybody is interested, they can register for which the course will be floated in the early part of 2019. So, what we are going to study in the particular section is called magnetic field assisted finishing processes, where we will see the first one is magnetic abrasive finishing. The second one we will see the allied process, that is called magnetic abrasive deburring, followed by magnetic float polishing, then magnetorheological finishing, and we will also see chemomechanical magnetorheological finishing process, and we move on to magnetorheological abrasive flow finishing process and rotational magnetorheological abrasive flow finishing processes. These are the things that we will see in the category of magnetic field assisted finishing process. So, what we are going to study in this particular section of magnetic field assisted finishing process, we are going to study magnetic abrasive finishing, magnetic abrasive deburring, magnetic float polishing. In this we will study in this 3 in this particular section, then followed by other processes where you will see magnetorheological finishing processes and magnetorheological abrasive flow finishing process and rotational magneto-abrasive finishing processes, and there is some variety that will be clubbed along with magnetorheological finishing processes called CMP, that is called chemomechanical polishing, and normally people uses the chemical to make a passivation layer, then remove by the magnetorheological finishing process. That glimpse we will see in the upcoming classes. So, you can see here magnetic abrasive finishing process, where the workpiece is rotating continuously and the abrasive particles are placed, where you have a north pole and you have a south pole, and the chains will form from north pole to south pole because of the rotation of the workpiece and other things. The shearing action takes place and the material will be removed in a nanoscale or sub nanoscale, and the surface finish is achieved in the nanometric range. So, magnetic abrasive finishing can be defined as a finishing process with a flexible magnetic abrasive brush composed of magnetic abrasive particles for the magnetic abrasive particles along with the CIP particles and other things. Okay. So, magnetic abrasive particles are prepared by the mixing of iron particles. Normally, iron particles are called as CIP, okay, carbonyl iron particles. These are normally very pure variety of iron particles. Okay. Whenever you have a magnetic field, so these CIP particles form the chain from north pole to south pole. Okay. So, assume that this is the north pole and this is the south pole. So, you will form a chain. So, these chains a multiple chains will form wherein abrasives are held. Okay, this is the one variety. And another variety of the abrasive particles is that you can go for the bonded abrasive particles, or in this aspect we can go for bonded magnetic abrasives using the sintering. That means that you have the iron particle wherein you can sinter the abrasive particles and you can make a single abrasive particle like this. Okay, this can happen and you can use this particular process for the finishing applications. Okay, normally unbonded also you can use. In that circumstances you have to form the magnetic particles chain, that is CIP particles chain, and you will have a abrasive particle, then you will have another chain. This chain will entrap the abrasive particle and give support to remove the material. You can see the working principle. This is the feed is given to the workpiece, this is the workpiece, and the tool is there, rotating magnetic pole plugs, and you have a flexible magnetic brush. You can see the north pole is there, south pole is there, wherein your workpiece is there, and you will form a magnetic field of lines. That is not the thing, but you form the chain. Okay, so these chains are formed and abrasive particles are entrapped. Okay, these abrasive particles are entrapped. These chains will support the abrasive particles, and since the motion is given to the workpiece as well as rotary motion is given to the tool, what will happen? The shearing action will take place. My workpiece is stationary and you are giving the table's feed, okay, and your tool is like this and it is rotating. So, relative motion causes the material removal. Okay. That is how the magnetic materials will help the abrasive particles to remove the workpiece material. So, for planar surfaces, whatever you have seen in the previous slide also is a planar surfaces, and workpiece is there, flexible magnetic abrasive brush is there. This is, you can see clearly the north pole and south pole where you have the magnetic abrasive particles are embedded in this one, and this field of lines will support the abrasive particles. Okay. And you can see the schematic of the bonded abrasive particle wherein ferromagnetic particle, that is nothing but the CIP particle is big one, and wherein you are going to bind or you are going to sinter the abrasive particles. Okay. This particular bonded abrasive will act as a single entity. Okay. So, whenever you are going to use, the previously you have seen it is for the flat surfaces. Now, if at all I want to see for a cylindrical surfaces, how it look like. So, now the cylindrical surface, I have the south pole, I have the north pole, and field of lines will transfer always between north to south. Okay. And you have the workpiece. The workpiece is given rotation, and because of this chain formation where the abrasive particles are there as well as your CIP particles are there, because of this relative motion, what will happen? External surface of the cylinder will be finished. Okay. And you can see here enlarged version the same image where you can see the abrasive particles which are nothing but the alumina Al2O3 is sintered on CIP particle. Okay. These abrasive particles will remove the material depend on the magnetic field strength. Okay. How to finish the internal cylinder? So, you can see the internal cylinder mechanism of material removal as well as what you have seen in the previous one, external cylinder. So, if you are seeing the external cylinder, what will happen is SiC particles are there, at the same time magnetic particle like CIP particles are forming chain, so that there will be a forces generation that is required, Fx and Fy, that is in the radial direction because of the magnetic field strength. At the same time, because of the rotational effect, there will be a tangential force. Because of this, what will happen? The material will remove on a cylindrical surface. So, if you see in the hollow cylinder, if at all I want to finish the inner surface of the hollow cylinders, in that circumstances what will happen, you have the north pole, you have the south pole, the field of lines will move always from north to south, that you can see here, and you have abrasive particles as well as you have the CIP particles. So, this is line of magnetic force will form the chains, and these chains will entrap the abrasive particles and finish the surface. And here also you have to give the rotational motion to the workpiece, because of the relativeness what will happen, the material removal will takes place. So, after seeing the flat surfaces as well as internal and external cylindrical surfaces finishing mechanisms or the schematic views, we proceed to the experimental setup, how to finish the simpler surfaces, because we want to understand the physics of the MAF process, then we have to go for the simple surface to be finished. So, in this particular case what we are going to see is a flat surface, how to finish a flat surface wherein the surface roughness is there. Okay. So, you can see here the electromagnet, the workpiece is there, as well as the dynamometer is also there. So, ring type dynamometer is placed on which the workpiece is placed. If you see this particular location where the workpiece as well as the tool is placed. Okay. So, the dynamometer is placed like this, on top of it there will be a workpiece, on top of it there will be the magnet wherein you have the flexible magnetic abrasive brush will be there. So, that flexible magnetic abrasive will form. Since the rotation is given by the variable frequency drive rotates the flexible magnetic abrasive brush, the spindle that connects to the flexible magnetic brush, that is called this one. So, it will be rotated by the variable frequency drive. Okay. So, the regulated DC supply is always given to the electromagnet, wherein the N as well as south pole and as well as north pole is there in the same picture. Okay. So, in the same tool you have north and south poles, and the electromagnetic field of lines will transfer from north to south. In between you just place the workpiece. Okay. So, you can do the finishing operation. So, elaborative way about the electromagnet we will see in the next slide. If you see the schematic diagram of the electromagnet which is act as a tool, what will happen is you have a south pole at the surface, north pole at the middle or the center, and you have the windings. Always there is a difference between permanent magnet and electromagnet. The people like BTech students, you may have some basic knowledge, you should have some basic knowledge about the difference between permanent magnet as well as the electromagnet. If you see a permanent magnet, the magnetic field strength will be constant, 1 Tesla. Assume that this the magnetic field maximum strength is 1 Tesla, means that is 1 Tesla completely. Okay. With respect to time, that may decay also. But in a electromagnet, what is the beauty about this one is you can control the voltage or the power supply, so that the windings will generate the magnetic field. So, the magnetic field can be a variable, it can be 0.1 Tesla, it can be 1 Tesla or anything. Okay. So, the capacity will be defined by your input power as well as windings and many other things. Okay. The difference what I want to say at this particular moment of time is that permanent magnet means you have a particular value of the magnetic field, and in an electromagnet you can vary the magnetic field. If you can vary the magnetic field, that means that your strength of your flexible magnetic abrasive brush can be improved. So, this is the north pole and south pole, and how it looks like in the practical way. You can see here, this is the south pole again, the red portion, and the windings are there at the center, and the north pole is at the core. Okay. So the specially designed electromagnet, which is a round and flat faced electromagnet, was used for the experimentation, and the dimensions are 76 mm diameter with a height of 50 mm is fabricated, and electromagnet has centered north pole whose diameter is 38 mm and surrounded with a coil whose thickness is 14 mm and further surrounded by a south pole which is 5 mm thickness. Okay. So you can see here, this is 5 mm thickness, and the 14 mm thickness is the windings, and again 38 mm is the north pole. So are the two poles sandwiches the windings in this particular thing. This is a special design that is made for the magnetic abrasive finishing. So now what will happen, always the field of lines will transfer from north pole to south pole. Okay. North pole to south pole, in that circumstances what will happen is you can give the relative motion so that you can do the finishing operation. That how to do the finishing operation, how the flexible magnetic abrasive brush will be formed and other things we will see in the upcoming slide. So as I said, the dynamometer also used here. The dynamometer is a ring type dynamometer, 2 Wheatstone full bridge circuit, one measuring the normal thrust force and another one measure the tangential cutting force. This circuit has 8 strain gauges. Normally this is a strain gauge type of thing. So you can place the workpiece and you can measure the forces. Okay. This may be ring type, may be normal strain gauge type also will be there. Okay. So there are some of the applications where you will use ring type dynamometer is like abrasive flow finishing process and other things. Here there also in a ring type dynamometer you will use a strain gauges. Here also you can use a strain gauge based. Okay. So the development of this type of dynamometers are economic, and you can maintain this one because you can fabricate with a little knowledge and a little collaboration with the electronics people and other people. Okay. If at all you want to go for a commercially available dynamometers, normally it costs you few lakhs rupees. That is why people go for the strain gauge based measurements. If you see the flexible magnetic abrasive brush formation in ferromagnetic workpiece material, ferromagnetic workpiece means it is a magnetic material. What will happen if you see the schematic diagram? The first one, the magnetic field of lines, you have at the central portion N, that is north pole, on other sides you have the south pole, because of which what will happen is you can form the north to south poles. Okay. Since you have the workpiece material also a magnetic material, because of which what is happening here is it is moving like this. So it is coming inside the workpiece also and going. That means that the energy or the strength of these chains will be very high. Okay. You can see the zoom up version of the chain here. So it has abrasive particles as well as iron particles, and you have seen the field of lines. And if you see the good picture of this practical experimentation, you can see the field lines. Okay. These are the chains that are forming. The magnetic CIP particles are forming the chains, and wherein abrasive particles are held. Okay. So this type of magnetic brush is generated which embeds the abrasive particles. So if you see for a non-ferromagnetic workpiece, in these circumstances what is happening here is you can see the north to south pole. Since this workpiece is a non-magnetic workpiece, so the field of lines cannot pass inside. So that means that the magnetic field strength is very low. Okay. So that is why the surface it has on the top itself the field of lines, magnetic lines of force, that is on the surface only. So there will be a slight problem that wherever the central portion is there, the finishing may not occur, but by giving the table speed, So, this particular central portion can be varied and you can do the finishing operation. If you see the flexible magnetic abrasive brush in the practical condition, you can see it is not touching. So, for that purpose it has to come. So, if you see the flexible magnetic abrasive brush, this particular portion for ferromagnetic material, it is very big and magnetic field strength is very high. For non-ferromagnetic material, it will be on the surface and the field strength is low. That there are some doubts that people will always get. If it is a magnetic material, there will be always chance that CIP particles may adhere to the surface. That type of drawbacks are there, but because of the relative motion of your tool, that is which is comparisons of north and south pole along with the windings, what will happen is that you can shear it off, okay, so that the finishing will takes place. Now, the difference between ferromagnetic and non-ferromagnetic material, you can see here, flexible magnetic abrasive brush is very strong in case of ferromagnetic, but not in case of non-ferromagnetic, and there will be adherence formation in the ferromagnetic, but it not in case of non-ferromagnetic, but both the cases depend on your application, you have to use this particular process. So, input parameters, mesh size of the abrasive particles, whether you want to go for 1000 mesh size, as I already said you that the mesh size conversion into the abrasive diameter, normally abrasive diameter is equal to 15.2 mm upon the mesh size. Assume that this is 1000 mesh size, what will happen is you are going to get approximately 15 micrometer, because if you convert the mm into micrometers, what will happen is 15,200 divided by 1000. So, it approximately boils out to be like 15.2 micrometers. Okay. The working gap has to be maintained, because in the flexible magnetic abrasive brush, in case of ferromagnetic is bigger, but in case of non-ferromagnetic it is smaller. So, you have to play with the working gap. If your working gap is too high, then the magnetic strength will be low. If you are going to have low, what will happen? The compression will come into picture. Not only finishing action will take place, but also it will scratch enormously. So, you have to play with the working gap. At the same time, percentage composition of iron particles, that is nothing but the CIP particles, because you required the chains to be formed. So, chains to the abrasive particles ratio should be always maintained. If your chains are more and abrasives are less, then also it will be a problem. So, your bonding strength will be very high. That means that the grade will be very high. Okay. That if at all you are going to have number of abrasives more and number of CIP particles less, then it will be a soft grade. Okay. So, the energy required per a particular particle by the CIP particles will be very less. That means that you have to play neither less nor more. So, you have to play with the experiments, or you have to do the trial and errors for get the optimum values of CIP particles as well as abrasive particles composition. And next one is input current. So, you have to give input current so that the magnetic field strength will be varied. Size of the iron particles. So, you have multiple types of sizes of the particles. You can go for bigger particles, if you can go for smaller particles, as all this will be depend on your application. Percentage of oil in magnetic abrasive fluid. What I mean to say is that you have iron particles, you have the abrasive particles. If you want to mix it, still I want a powder form. I do not want like a liquid. Okay. Liquid type of magnetic fluids that we will see in the advanced version, that is called magnetorheological finishing processes and magnetorheological abrasive flow finishing process and other things. But here, to make a consistent or to make the proper bonding or to make the integration, for that purpose very little amounts of oils to be used for this particular MAF process medium. Okay. So, I have the CIP particles, I have the abrasive particles wherein I am going to mix a very little amount of silicone oil or very little amount of grease or something, then it will be easy for me to make this particular particles type of fluid, because whenever you do apply the magnetic field, what will happen is that you have to form a proper chain. If it is a different entity, then the chain formation may be a problem. If you have some oil so that the connecting between the CIP and the abrasive particle is good, that means that the chains formation will be very good. For that purpose, you have to use the optimum amount of oils. If the finishing time is high, so the more and more number of peaks will shear. So, you will achieve the critical surface roughness. Once you achieve the critical surface roughness, then you can remove it. Abrasives used in this particular process. So, abrasives normally one can use, the abrasives can be used is silicon carbide, Al2O3 and so on, you can use as per your requirement. So, output responses, normally this particular process is a super finishing operation or a ultra fine finishing process, where you always go for the surface roughness criteria. That means that the first and foremost criteria that you are going to look is what is the surface roughness or the surface finish that I am going to achieve. Second one is the material removal. So, we may not bother much about the how much material is removed from this particular surface, because our primary concern is surface roughness. The forces, as we have the dynamometers where the strain gauges are fixed and it will give the forces and other things. If the forces are very high, so the indentation will be very high. That means that the surface roughness you may get is not up to the mark. So, if you can control the interaction forces between abrasive particles and the workpiece surface, that means it is always good. So, surface morphology, many times people will think about the surface morphology and surface roughness are similar or something. Many cases people think about the surface morphology and surface roughness are integrated. It is true that both are integral part of each other, but for the same surface roughness you may get different surface morphology. Okay. So, there are many examples for, assume that I want to get 1 micron surface roughness, you may get the 1 micron by grinding process, 1 micron you by the fine boring process, 1 micron you may also get by fine turning process also, but the morphology will be different. Okay. That means that the surface patterns will be different, your lay pattern will be different. As I said, lay is nothing but the predominant surface direction or predominant surface roughness directions, this will be different. So, you can also get 1 micron by honing process. So, you will get a crosshatch pattern in one case, you will get a triangular peaks in the turning process, you will get a straight lines in the grinding process. Okay. That means that surface morphology also play a major role for your application. Application to application, the surface morphology will be changing. You cannot use the grinding morphology or the turning morphology for the engine cylinder. There you have to use the surface morphology of honing process only. Okay. Magnetic abrasive finishing, where you see the flux density. Magnetic flux density is measured at various distances from the outer surface of the magnet toward the center of the ferromagnetic and non-ferromagnetic materials. So, magnetic flux density 3 times higher in ferromagnetic workpiece compared to non-ferromagnetic workpiece. Okay. If you see the non-ferromagnetic workpiece, the maximum that is achieved is 1200, but in case of ferromagnetic material, it is approximately in between 3500 to 4000. Okay. But at the same time, you can see it is observed at the central portion. Okay. The distance from outer surface to towards the magnetic center. Okay. So, you can see the maximum the flux density is achieved in the ferromagnetic material, that means the magnetic material. So, that means that field strength is very high. Even though surface is very rough or slightly higher side also, you can do the finishing operation. Okay. So, magnetic abrasive finishing process, you have two varieties of flexible magnetic abrasive brush. One is static flexible magnetic abrasive brush, another one is pulsating flexible magnetic abrasive brush. In the static flexible abrasive brush, what is happening is that whatever you have seen till now, all will come under the category of static one. Okay, because your power supply, DC power supply is constant and you are going to get a static one. So, your chains are not relieving. So, that means that whatever the pictures that you have seen in for a ferromagnetic, for non-ferromagnetic, your chains are formed and your tool is rotating and the workpiece is giving the feed by the table. So, whatever you have seen is a static flexible magnetic abrasive brush, and the pulsating type of flexible magnetic abrasive brush you will see in the upcoming slides, and what is the advantage of pulsating over the static we will also see. Okay. If you see here, the formation of flexible magnetic brush is constant in this one, but if you see the in terms of the static one, your chain is fixed. That means that chain formation will be always there, so that abrasive particles are there embedded in the chains. But in the pulsating one, what is the beauty about it one? You are giving a pulse, then again you are giving a power. In that circumstances, when there is a lag between two pulses, what will happen is your flexible magnetic abrasive brush will collapse. So, if it collapses, you may think that it is negative, but if it is collapses, what is the beauty about it is your abrasive particles can reshuffle whenever it is forming a second chain, but this particular collapsing and forming the chain, there will be a very little gap. That means that you have a microseconds gap or a nanoseconds gap in between. What will happen? There is a always chances that as soon as the chain collapses, the abrasive particles also will disorient or dismantle from the chain, because of which what is going to happen is that your abrasive cutting edges, new cutting edges may emerge for the finishing operation. That is the beauty about pulsating flexible magnetic abrasive brush. If you see the comparison between pulsating and static, the surface roughness achieved in static and the pulsating are completely different, and this particular thing is achieved by the virtue of or the by application of the pulses. Whenever you are going to give the pulse current, what is going to happen is that your chain, CIP chain is collapsed and the abrasive particles are oriented or reoriented. According to that, what will happen is new cutting edges or new abrasive particles will come into picture and the finishing will take place. So, you can see here percentage decrease in RA for the static flexible magnetic abrasive brush is approximately between 30 to 35, but if you see the flexible magnetic abrasive brush, the maximum it can go up to 60% also. Okay. That is the beauty about this one. That is the beauty about flexible magnetic abrasive brush. Okay. So, why it is achieving? Because the chain is collapsing, and whenever it collapses, the abrasive particles changes. First point, abrasive particles may reorient and the chain in the second time formation may be better chain. or many possibilities are there in the pulsating type of flexible magnetic abrasive brush. Okay. You can see the before and after the magnetic abrasive finishing process. Here it is not at all visible here. You can see NUAA, it is not at all visible because your surface roughness is too high. However, after finishing you can see it is clearly visible all the words. Okay. So, that is the beauty about the surface, and you can also see the scanning electron microscopy image of these things. If this type of surface is there, what is going to happen is you cannot see the mirror image. If you are going to polish it, then you can see the mirror image after MAF process. These are the results that are taken from Professor D.K. Singh, who is a student of Professor VKJ, and you can see before and after for the ferromagnetic and non-ferromagnetic materials, and along you can see the better surface finish that is achieved in the non-ferromagnetic is 0.06, but in case of ferromagnetic stainless steel you can see it is 0.04 micrometers. Okay. So, you can see here for the non-ferromagnetic stainless steel and ferromagnetic stainless steel that the before surface roughness and after surface roughness, what is you are going to achieve is, in case of non-ferromagnetic stainless steel, the initial surface roughness is 0.28 microns. After surface finish using magnetic abrasive finishing process, the surface finish is achieved is 0.06 microns. In case of ferromagnetic stainless steel workpiece, if you see it is 0.25 microns is the initial surface, and after it is 0.04. Okay. This is attributed towards the strength of the chains, the strength of the chain that is formed during this process. As we have seen in the ferromagnetic, the chains are embedding, or it is also going inside the workpiece material and forming a very strong force of magnetic force of lines, and this forms a strong chains and the abrasive particles are embedded and the finishing is proper. And not only in this condition, non-ferromagnetic also this will be very good. Okay. So, now we will see the application of this magnetic abrasive finishing for the deburring applications. Okay. That is why some of the scientists it is called as magnetic abrasive deburring process, but this is similar to the magnetic abrasive finishing process, wherein your application is different. In the previous case, your major aim or the objective is to get the surface finish. In this case, your objective is to remove the burrs that are generated in conventional machining processes that are used before magnetic abrasive finishing process. Okay. First, as I explained in some of the slides, burrs and other things. Okay. Still some of the people may have the doubts how the burrs look like, what are the burrs and other things. So, that particular thing I want to clarify. For that purpose, I have given you especially one slide. Okay. It is normally seen in case of drilling operation. So, for that purpose, we have taken from Sankey, Min et al. Classified the drilling burrs into three varieties. One is uniform burr, and second one is a cone burr, and the third one is a transient burr. If you see the uniform burr, it has a relatively small height and thickness around the whole periphery. You can see here. And the second one is a cone burr. It has a larger and irregular height distribution around the hole. Okay, you can see here, and it has a irregular surfaces. Okay. So, at the same time you can have a small type also. The transient burr formed in the transient stage between uniform and the cone burr. Okay. Cone burr is what we have seen here, and in the transient burr it is neither a transient, it is neither a cone nor a uniform burr. So, it is like this. These are the burrs that you generally see in a drilling process on the back side of the workpiece. If you are going to drill a through hole and you may not remove the chip which comes at the end properly, and this will hamper the operators, or this will hamper if you are not going to remove it. This will hamper the customers who are handling these particular components. If you have this uniform burr, chrome burr and transient burrs, and if you are using this one with your hands, what will happen? These materials which are made up of stainless steel or some other things, what will happen? This may cut the hand of the operator or hand of the customers. Okay, this also hurt various parts of the operators if it falls and other things. That's why you have to remove these burrs. Okay, that removing of the burrs from the sample or from the workpiece is nothing but the deburring operation. Okay, dehydration for some people, if at all you want to remember in a good way, so you can say like dehydration. So water is removed or it is going out or something. So similarly deburring, so that means that burrs are removed. For the same, as I said, we are going to use the same experimental setup that we have seen in magnetic abrasive finishing process, and the slight change that we are going to do is that we are changing the fixture. Instead of going for a big workpiece, we are making a slot in between. In case of magnetic abrasive finishing, we can finish this particular complete one. Okay, but if at all I want to remove the burrs on the flat surfaces, what I am going to do is that we are going to place the holes drilled surface. This is my workpiece, or this is my workpiece wherein I am going to drill a hole or set of holes I am going to drill, and these holes will have the burrs. Okay, assume that we are going to consider one workpiece material, that is called brass workpiece. What you have to place this particular sample here and tighten it using proper screws, then you are going to feed to the magnetic abrasive finishing process. So that means that you are going to have your workpiece here. If you see this particular assembly, that you have the fixture here and you have the workpiece here. Okay, so the burrs are there and these burrs are to be removed. Okay, so we will use the similar setup, that is MAF process. For the plane surfaces only we will use, because we want a plane surface. For that, only requirement is that you have to remove the burrs so that you will get a flat surface, and you are going to give the rotational speed as well as feed rotational speed to the magnetic tool, and the workpiece will be given feed so that you can remove the burrs. So you can see the burrs, these are the burrs which are removed in the case of second case. Okay, you can see some of the burrs that are not removed from the drilling hole. These are the burrs before deburring operation, and after deburring operation you can see there is no burrs on the flat surface. Okay, you can see the complete hole after drilling process, and you can have the burrs on the surface. The drilling can be done by EDM process also, and EDM also can create a recast layer and the corresponding burrs also. Okay, it is not only the burr formation is not only specified for the conventional, it is also for the advanced machining processes also. And you can see clearly the surface, the burrs formation, and later it can be removed by the magnetic abrasive finishing process, and particularly it is for the deburring application. what I mean to say is magnetic abrasive finishing is used in this case for the magnetic abrasive deburring operation. That's why this particular process is called magnetic abrasive deburring. Okay. The another process that we are going to see in a introductory way is magnetic float polishing. Okay. Many of the people may not be acquainted with this particular process because this particular process is not much done research. So, some people who want to do into this particular process as a research, they can take up and they can do a very good job. So, magnetic float polishing process, if you see the magnetic float polishing process, the magnetic poles are arranged into north south, south north like this. At the same time, you have the workpiece materials is the ceramic balls and you have the magnetic fluid. You are going to have the spindle and these are the ceramic balls, these are the spherical balls. Okay. The spindle is given the pressure and rotation motion, and because of the north and south, what will happen, the chains will form and these chains will press against the workpieces, that is the ceramic balls, and you have levitational forces and other magnetic forces, so that the finishing will takes place. Key features of this particular process is finishing process which are controlled externally by the controlling the magnetizing current. That means that your chains are controlled by the magnetic field. At the same time, Si3 N4 balls are roller. These are the ceramic balls which are non-magnetic workpiece materials, and these can be finished using this particular process. What I mean to say is that if at all you want to finish a spherical surfaces, you have to opt or the best process to finish into a nano surface level like 4 nanometers average surface roughness value, then you have to choose magnetic float polishing process. But it has its own limitations, that is a shape limitation. Basically, it can do for spherical and cylindrical as external surfaces only, and it has a size limitation. You cannot go for very big workpieces and other things. But this particular process is least explored, and people who want to do their PhD or masters and other things, they can work on this process, and if you can develop this process and if you can do, that will be a good research work. So, the summary of this particular class, we have seen introduction to advanced abrasive finishing processes, then we move on to the introduction to magnetic field assisted finishing process. What are the finishing process that comes under this particular in the category of magnetic field assisted finishing processes, and basics of magnetic abrasive finishing process, then how the magnetic abrasive finishing process is applied for ferromagnetic workpieces as well as non-ferromagnetic workpieces. In ferromagnetic workpieces, how the magnetic field of lines or the magnetic force lines will be formed, and in case of non-ferromagnetic material, how the magnetic field of lines are formed. These are we have seen, and what is the finishing capabilities we have seen, and how the flexible magnetic abrasive brush is formed in case of the non-ferromagnetic workpiece material, how the flexible magnetic abrasive brush is formed in case of ferromagnetic workpiece material we have seen, and the magnetic abrasive deburring, just it is a variant of magnetic abrasive finishing process, wherein just you are going to add another dimension to remove the burrs that are generated during the conventional as well as unconventional drilling processes. Okay. So, some of the people they are also using this magnetic abrasive finishing using the chemomechanical also, that is called chemomechanical magnetic abrasive finishing process. In chemomechanical process, what is going to take place is you are going to add some chemical that are going to make a passivation layer on the workpiece surface, okay, so that the surface will become smooth and then you can remove that smooth layer. So, people are working on this one. So, some of the people who are interested for doing research and other things, they can go and they can take up this challenge like a chemo-mechanical magnetic abrasive finishing, which is slightly advanced version of magnetic abrasive finishing process. Okay, that is another variant of magnetic abrasive finishing process apart from magnetic abrasive deburring. If you can also do the chemo-mechanical magnetic abrasive deburring, that will also will be fine. And at last we have seen the glimpse of magnetic float polishing. As I said, magnetic float polishing is not much explored. So, people can follow Professor Rangakumanduri's papers, who extensively used magnetic float polishing, and if at all the people want to study about magnetic abrasive finishing process, magnetic deburring process, you can follow many papers of Professor Vijay Kumar Jain of IIT Kanpur. Okay? Thank you for your kind attention.